This one is an assignment related to gravitational field, Newton law of gravitation. The question two, that is Jupiter is the most massive planet in our solar system. In 2016, the spacecraft Juno completed 5-year mission to Jupiter, and it's currently orbiting the Jupiter with a period of 14. Calculate the radius. So if you want to calculate the radius, say this is representing a Jupiter and a satellite is orbiting with a time period of 14 Earth days. So, and the distance, this radius is always from center. Remember one thing, like center of the, between the center of the mass of the two objects. It's not from the surface, it's from the center. So that is radius of its orbit, we say r. So what happened as it is moving in a circular path, so there is a centripetal force, and because the gravity is acting, so the centripetal force is equal to gravitational force. The centripetal force is given by a formula mv square over r or mr omega square, where r is a radius and omega is the angular frequency. And the gravitational force is given by formula g, the mass of the Jupiter m, the mass of a satellite small m, divided by the distance between them, their centers, and then square. Now we simplify this equation, so m will cancel with m, and this r square, it will go there, it become r cube. So we'll have r cube is equals to g, the gravitational constant, m is the mass of a Jupiter, divided by omega square. And how to work out omega? Omega is equals to angle, if there's a one complete revolution, that's 2 pi divided by t, the time period. So omega will be equal to 2 pi divided by time period. That's 14 days, but it should be in second as omega is there, radian per second. So this will be 14 times, we have 14 days, and then we have to convert these, because it's 14 days, so we have to convert. And one day, the number of the seconds are given already. So like it's mentioned here, one day is having 86,400 seconds. So 86,400, we just multiply them and 2 pi divide by the answer, we'll get omega. So just substitute the value of the mass of Jupiter, the gravitational constant omega. So we'll get the radius of this satellite. In part B, the diagram shows the Jupiter and the Sun at a point where the gravitational field strength of a Sun is equal and opposite to gravitational field strength of a Jupiter, and that point is labeled as P. The mass of a Sun is ms and the mass of a Jupiter is mj. The gravitational constant is g. State an expression for the gravitational field strength of a Sun at a point P and a gravitational field strength of a Jupiter at point P. So what's a formula which relate the gravitational constant g is equals to capital G m over r square. That's a formula of the expression which we use to work out the value of the gravity at a certain point from the planet. We just have to write the expression for the gravity of the, where m is the mass of the planet, which, or the mass of that astronomical object which is creating that gravity. So if we talk about the Jupiter, so from Jupiter, if we want to find the gravity of the Jupiter at, like the strength of gravity of a Jupiter at this point, like G and subscript J is there. So capital G, the mass of a Jupiter, divided by this distance is r, so it will be r square. And as I mentioned, we take always the distance. But for Sun, the gravity of the Sun on or that point, Sun gravity is also acting, so gravity of the Sun is at that point is equal to G. The Sun is creating that gravity, like responsible, so mass of Sun, and divide by like distance square, so it will be r is the distance between the center of Sun to that point, so it will be r square. So these are the two expressions. The next part, show that the ratio of r, capital R over small r is about 30, and mass of a Sun is given, mass of a Jupiter is already there, And we wrote these two expressions. Uh, we have these two expressions. The gravity of the Jupiter is equals to capital G, the mass of a Jupiter, and small r, and the gravity of the sun at that point P is equals to gravitational constant mass of sun over r square. And at that point P, the gravity of the Jupiter is same as the gravity of the sun. So we can say gravity of the Jupiter is same as the gravity of the sun. And gravity of the Jupiter is capital G, the mass of a Jupiter, divided by r square equals to the gravity mass of a sun over capital R square. Capital, like the gravitational constant, will cancel out with each other. This r square is divided, other side will be multiplied. So it will become, so this will be r square over small r, capital R square or small r square, mass of sun divided by mass of Jupiter. But we need like ratio between r, capital R or small r. So we take a root to cancel out this. So capital R or small r is equals to under root the mass of the sun divided by mass of Jupiter. So mass of a sun is 2 into 10 power 30 kg. And the mass of a Jupiter, that was there in the first part, like the beginning of the question, when we solved the part A, that was 1.9 exponent 27. So this will be 1.9 into 10 power 27. And we take a root. So this will give us the ratio between capital R or small r, which is about, it should be about, as I mentioned, it's about 30. So our answer should be around 30. So it's about 32. Hence, calculate r the distance from a center of a Jupiter to the center. So how we the distance from center of the Jupiter to the center of the sun is 7.8 kilometer. So 7.8 exponent 8 kilometer. So we work out this r, like basically what is the equation? The equation is this total distance from here till here, it is 7.8 into 10 power 8 kilometer. And we know that the ratio between capital R over small r is equals to 30. So we can say r is equals to 30r. So means the capital R is equals to 30r. So r plus small r plus capital R is equals to 7.8 into 10 power 8. And capital R is equivalent to 30r or 32r according to your calculation. So if we say 30, because the ratio for us it was 32. So we'll say 32r, 32 small r, and then we simplify like divided by 33. So this will give us the distance between the Jupiter and the point P. One function of Juno is to monitor the temperature for Jupiter atmosphere. At the top of atmosphere, the temperature can reach about 725 degrees and determine the type of electromagnetic radiation that the instrument in Juno must be sensitive to, and your answer should include a calculation. So how we can identify which type of radiation? According to Wien's law, with the temperature, we can identify which type of wavelength, which wavelength are emitted out. So the product of lambda and temperature is equal to 2.89 into 10 power minus 3. This is a Wien's law, which is showing a relation between the temperature and the wavelength. But temperature should be in Kelvin, so we should add 273 to this. So we convert this into Kelvin. And then we'll work out what is the wavelength. So wavelength, the wavelength is equals to 2.89 into 10 power minus 3 divided by the temperature, which is 725 into 10 power 725 plus 273. So this will give us the wavelength, which is 2.9 exponent minus 6 meter. And this wavelength correspond to in IR, because as this is a longer wavelength, because 10 power minus 9 or nanometer or if it is in micrometer, because it's for zero point 0.4 into 10 to the power minus 6 to 0.7 into 10 to the power minus 6, that is a visible, or like the range of a visible light. This one is a red, this one is violet. Violet is having a shorter wavelength. So this is a range of the wavelength. But because this 2.9 exponent, so it's a longer wavelength, so longer wavelength than red, it means this is infrared. As we have an electromagnetic spectrum, violet, like the radio waves, microwaves, radio, micro, IR, the infrared, and then we have visible, which include red to violet. So this is 0.7 and this one is zero point 0.4 nano micrometer. But this one is is more than, because in this order the wavelength increase. So it means it should be IR or infrared radiation. Is it clear, this one? Question?